Hello and welcome back to Calculus 3, section 11.5, lines and curves in space. So you are used to functions in 2D, and at one point I mentioned that now the world of 2D is going to be laid out on the floor, so you can follow the trace of sine function if you walk, or whatever line that you stretch and draw, right? It will be function, not function, whatever, would be on the floor now. So what happens when you have a 3D line? I'm going to pull out the string. So how do we describe this? As you can see, it's curving in all possible ways. Now, sure, we can, shine the light, get the image, and maybe figure out something on the XY plane. But I want to take a look at this particular line and somehow describe it as a path, because this might be the path that particle takes, or path that, I don't know, whatever. So we would like to be able to describe these. And then these paths will relate to your parametrization. So technically what we are doing now is we are going to define something that's called vector valued function, and that is actually going to be a vector of parametric equations for 3D, right? Well, 2D first and then 3D. So vector valued functions, we start there. So we'll start with a notation where this could be actually any dimension, because vectors are not restricted to be 2D or 3D. But we only use the parameter t as the input. So this is going to be a vector that will have 3 components, and all 3 components are functions. So now, what this is this is the set of parametric equations in 3D. So set of parametric equations in 3D. And we have 3 dependent variables, f, g, and h, right? Which depend on the independent parameter t, which is shared between all of these. Now you can look at that t as time, right? So that's as time flows, the progression along the line happens. So if we put the ant on this curve in space, which definitely, because ant can't fly, it will be bound to walk on the line. So I can say at t equals 0, ant starts here, and then if the ant goes all the way to the top in one shot without going around and doing anything weird, we can just measure how long that took and maybe call that, say, 10 seconds, t equals 10. So the progression, the parametrization of this will be whatever functions need to be there to describe this curve, but then that parameter t can be thought as the time that took. So now you can say what happened at t equals 1. That corresponds to t equals 1 second, which is f of 1, h of 1, and g of 1 and h of 1, which actually would be a location, and say after 1 second the ant is, let's say, right there. So that's technically what's happening with these vector valued functions. Now, to understand this, let's just draw something. So we have x, y, and z, and then I have my line L, that is described by this vector valued function R. Now, if I want to make it a finite piece, I'll have a capital A and a capital B, and I'll say that this is, let's say, t equals 0, and then this could be some t equals, I don't know, I mentioned 10, so here we go. Now, these are seconds or hours or minutes or decades, whatever. You put a snail there, it's going to be a decade, right? So, the most basic thing here is to understand that you are actually plugging stuff in. So if I have an example that, let's say, r of t is equal to t plus 1, t squared, and 1 over t, in which case I can't use 0 because of 1 over t plus 1. There you go. Fixed. Now you can. So let's say this is your vector valued function. You can ask yourself, so where is this point A, right? Where? And that point A is going to be at r of 0. So what you're doing is you are technically plugging in 0, 0 plus 1, 0 squared, 1 over 0 plus 1, and you will get the vector, which is a location. So 1, 0, 1. It's a location. Now it is actually, you can see that this A, I did not put the arrow on top, I should have. This is that vector, now, vector A. So now, why is this vector valued function called lowercase r? Well, it's like a radius, right? It sits at the origin, which is like the center of the universe, okay? And then it kind of stretches itself to follow along every single point along this curve. That's what radius does, to follow the ellipse, that follows the circle and so on. So in this case, lowercase r is going to do the same thing. So when you write it as a vector valued function, you have the set of 3 equations, and those 3 equations describe every single point that you can come up with. We're talking t equals 1.3, t equals pi over 7, and all that stuff. There you go. Good. So we have all 3 of these. All 3 of these. Stop stealing 3 times. One steal, like infinity of points, not 3 points. So all infinity of points between time at the beginning and at the end. Do these lines have to be finite? Hell no, right? But for the purposes of, engineering, stuff is finite. All right. So you have a vector valued function. Vector valued function is just a fancy name for pile, right? The vector of 3 parametric equations. One that explains x, y, and z. That will compute x, y, and z location. So 1, 0, 1 in this case is the terminal point, and then there is a vector that is stretching from 0 to the terminal point, and that vector is the vector I computed. I can plug in 10, that would compute vector here, or you can come up with 4.6, let's say, would be there, and so on. So you can come up with any calculation. It is just plug it in and move along. So with this, we can describe any curve in space, and we generally stick with those that are easy to compute. So the easiest form of this would be the straight line, which is a linear line in space. So let's take a look at a straight line. So straight lines. From this point on, you will have some equations that will have multiple forms, a vector form, and then, well, we'll see. All right. So what do we have? We have our good old x, y, z 3D coordinate system. We are going to have a line L. We're going to pick 2 points on that line and stretch these 2 vectors that go to those points. This is P0, which is x0, y0, z0 as a location, and then just point P, any point, which is x, y, z. Now, we have these vectors. We have this vector here, which is a vector r0, and this vector contains its x0, y0, z0. So, guys, I'm hoping that you are studying enough to understand the difference in the notation. Because if you start confusing this and you never fix it, you will be doomed. There we go. I found a way to plug it. So look, this is location, point, regular parentheses, x0, y0, z0. So you're thinking here 113, right? It's a location in space. It's a single point in space, and that's it. The vector will have the same coordinates, 1, 1, 2, or 3, whatever I said, but now it's a vector which represents the line that stretches from the origin all the way to that location. So, point and this are different, right? Point is different from a vector, even though they have very similar notation. So, be careful. Regular parentheses or spiky, right? Parentheses, spiky ones are used for vectors. That's the red line that stretches. And regular parentheses for point, which is just the location. All right. Now, what is the equation of the line? This is major. R is equal to R0 plus dV. Vector, vector, vector. All right, stare at the screen because I need to show something. Ready? Y equals M X plus B. And then we'll talk how they're compared. One more time. I'll use the arrows now. Y equals M X plus B. I'm going to erase that eventually, but the form of the line remains the same. Never mind you are in the 2D space, 3D space, 10D space. A line is a line, a simplest creature in whatever dimensions you have. And this is a vector equation where this R can take any number of dimensions. You see that in this case over here, R is taking 3 dimensions, x, y, z. But there's nothing that prevents me from having 25 dimensions if I want to. This is the major line. And then, if you decide to go down to the 2D, you will use I2 and so on. Now, looking at this, you have the final location is equal to initial location plus the tilt, right? So, the straight lines now in space don't have slope. This vector B is equivalent of the multidimensional slope. Because when you are in 2D, which is the board, I only have this to play with. So we know that positive slopes, right? Zero slope, horizontal, negative slopes when it goes down to the right. But now, I can have the same motion like that in 3D, but then in addition to that, I can have all of this, right? And any one of these locations here, right, is the location that is described by vector V. So vector V is that kind of 3D slope, 4D slope, 10D slope, whatever the dimensionality of the equation is. And these two are simply 2 points. And then time. That's the input variable. So, you see that the form of the equation is the same. Now what I'm going to do is I'm going to break this apart over its components and write it as a parametric set of equations. So this is the vector form. And now I know that vector R is x, y, z. I know that R0 is x0, y0, z0, t, and then we have a, b, c. I did not mention that before, but now there you go. So I can expand the formula into this, and then from there write the parametric set, which is x equals x0 plus at, y equal y0 plus bt, and z equals z0 plus ct. This is the parametric form. And then from here, one more. Each one of these has t. I can solve for t in each one equation and then write three-sided equality for equation of the line. So, if I solve the first line for t, I get that t is equal to x minus x0 divided by a. T in the second one is y minus y0 divided by b. And finally, t equals z minus z0 divided by c. Those give me that x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. That is yet another way to represent the line. I don't know what the name for that one would be. Exploded form? Whatever. Do they even have it in a book? They should. They have it in Larson, I know. It's just another way to represent, right? That's the. Sometimes actually problem is given in this form. Yeah. Hey, less writing. You didn't have to write T 3 times to save some ink. Also ABC, which is that 3D slope, is easily visible. Look at the denominators, ABC. And that ABC is going to be extremely important down the line. So that's the form where you pick it up easiest. Okay. So now, red, line segment, line segment, yeah, line segment, I'll just say we use T1 less equal than T less equal than T2. So we are using, and that's what I had before, 0 and 10, right? You're using finite value, infinite line, infinite line, we use negative infinity, oops, can't do the less equal, less than T, less than positive infinity. So if you have restrictions on T, we know that it's a line segment, finite line. And if you don't have restrictions on T, the line stretches forever. So let's take a look at an example. Haven't done any numbers yet, so let's take a look at those. So I'll pick up something from homework, obviously, because you guys know the letters. You can read the example in the book. So number 14 says find the line, well, find the equation of the line through 101 and 3, negative 3, 3. So you have 2 points in space, and they want to know what is the line that goes through this. Obviously, you have 3 different forms of the lines you can put in any one because they did not request a particular one. So anything is fine. What now? Exactly. What should we do? Where do we start? Yes. Yeah, but I need the equation of the line. You are right that the line is infinite. Yes. Yes.
101 and with the point and then do that equal to x0. The if x, y, z equals to x initial, y initial, z initial, plus t
Okay.
times,
Times what?
yeah, and ABC.
Yeah, but we don't have ABC. And we need them. What vector? Yeah, but what do you get? I mean, sure, we can do that.
So we can make up the t.
We can also add 1 plus 0 plus 1 and get 2. What is the goal of doing that? Subtracting the two vectors. Do we go 3 minus 1 or 1 minus 3? Or it doesn't matter? Yeah, but what vector do you get? And what's the significance of that vector between 2 points? Ah, there we go. Cool. So yes, and that's the reason. So, do you remember how to find the line in algebra? This one, I'll tell you one of my secrets. Why am I so godly in mathematics? When I see new concept, I just want to know if that concept was introduced somewhere in earlier, right? In much easier form. So immediately I go and I say, okay, when I have 2 points in basic algebra, I use those 2 points in the y2 minus y1 over x2 minus x1 to get the slope. So subtracting coordinates in algebra gave me slope. And then I use that slope with the point to come up with the rest of the equation. So this has to be the same. It has to be the same method. It's just now you are doing it in a 3D. So I need this 3D slope. If these 2 points live on the same line, then when I subtract their coordinates, I'm going to get a vector between them, and that vector is the carrier of the slope, right? Which way the line goes. So this air quotation mark 3D slope. So if I have that this is a 1, 0, 1, and this is 3, negative 3, 3, the slope in between them will be that slope v, which is the 3D slope. So yes, we get vector v by subtracting these, which is 2, negative 3, 2, and then we have the first point, right? The initial point is 1, 0, 1 because we said 3 minus 1. So that's the initial point. We have our equations. So x, y, z is going to be 1, 0, 1 plus 2t minus 3t plus 2t. So we can write equation of the line as 1 plus 2t, negative 3t, 1 plus 2t. This is the vector form as a vector valued function. You can also eliminate parameter t equal them all, right? It will be x minus 1 over 2 and so on. Or you can leave them as a parametric set because the problem did not specify. So I gave you 2 alternate ways. You don't have to put a 0 there. I gave you the 2 different ways of representing the same answer. The only one that I didn't write is the one where you eliminate t, but that one is easy to see, right? It will be x minus 1 over 2, y minus 0 over negative 3, so just y over negative 3, and equal to z minus 1 over 2. Yes?
So the R0 is 1, 0, 1?
Yes. R0, yes. R0 would be the vector that stretches from the origin into 1, 0, 1. Yes?
What was divided by A, B, and C again?
It's just another way. So I gave you 3 different ways of writing the equation of the line.
Yeah, that's the x0 minus x.
Yeah. So That's the one where you can easily see A, B, C, pick it up easy, and that's what is the that 3D smoke. Right? Whether you want to go like this or like this or like that. Right? Yes. Yes, but then you have to turn your read. So if you pick 3, negative 3, 3 to be your initial point, then you will be doing subtraction the other way. And when you do subtraction the other way, the minus signs will pop in, and you'll have another one, so the other result is the same. Remember that you are not allowed, when you're doing slope, you're not allowed to leave x and y, right? You have to go y to minus y1, and then x to minus x1. You can't go y to minus y1, and then x1 minus x2, right? So whatever you pick to be initial point has to be initial point to plug in and to have to do it. Yeah.
When we run a vector form like that, or everything within the pointing,
Yes? Vector value function.
now that, so I'm looking, that's kind of just like circular, just have the y.
Yeah. Yeah. So the let me just get all three of them on the same. So this form over here, if you are to write it as R equals, like this way, or that way, it's just three different ways to write the same thing. The way I wrote it is the way that it's used most of the time. So I would say 90% of the time, it will look like this. Because, yes, for the lines, you can stack them up, right, as a parametric equation. But we usually stuff those parametric equations into a vector. And vector is like a matrix, right? A rectangular array of stuff, right? Where you put numbers, you put functions, you put whatever. Object. So when you describe a straight line, you have the three different forms. But then for other lines, you know, this or this, but this is less writing, right? Over here you only write one equal sign. Over here you have like two extra. I don't know what to tell you. It's just that most of the time you will see the answer given in parametric form written like this. But this is also parametric form, you know, from chapter 10. You will not be wrong writing it either way, except we kind of always gravitate towards the one on the bottom. Okay, before I break your head thinking, let's see. Ooh. Shall we? Yeah. All right. 22. I find the equation of the line through zero to 1. That is perpendicular to both vector u, which is given as 4, 3, negative 5, and the z-axis. Good luck. This is the time when you will be glad to know some people sitting next to you so you can discuss. Plus, you avoid that embarrassment. When I go around and I ask you what's his name. All right, let's do this. Like you would say, just do it. You guys saw the labs are uploaded, right? All 5. You can just imagine that, technical awful things I have to say that after that crazy. All right, who's done? Imagine you're seeing these problems for the first time on the test. How would you deal with it? Consult notes. The time when you show off your knowledge. No.
Knowledge, notes,
Oh, the replacement problem? Oh, you jumped right on the last page. Yeah, for all the newbies over here, some of the exams have replacement problems. So you get 10 problems to work on, and then 11th problem is like a replacement problem. So let's say you really, after 3 hours of thinking, can't remember how to do problem number 5, you might slot 11 for that problem. You have to write down. What if I write a vanilla exam, I don't have to put the 11 problem? Where do we start? I mean, what are you thinking about? Hopefully, that way. Like one is like, I'm thinking how all kinds of ways to kill you right now. Why are you sharing what I know? Yes.
Assuming that R0 is 021.
Perfect.
That's all I know.
All right, so we identified that. That's good.
Well, I found out the line, and I'm just trying to not get confused with sometimes.
All right, I'll check.
I don't know until we're figuring out the line, but I know, or at least I think we have to take a cross product, because we want perpendicular.
That was a given.
How will that given?
It's just perpendicular, buzzword.
Aha! So now we have buzzwords. The word perpendicular triggers cross product, like that. We said that two vectors create the plane. If the two vectors create the plane, well then, the cross product of the two will give us, but how do you write the z-axis? 0, 0, 1, that's the k vector, yes. So, cross product, very good. Cross product between 4, 3, negative 5 and 0, 0, 1 will give you the vector v, in this case, vector v, the slope, right? because that's the answer from the cross product is the line that is perpendicular. So your slope is the perpendicular line, that's the cross product. You have R0, so let's go. You have 17 seconds, no pressure. Yeah?
I'm stuck in the last part of the problem.
I'll be right there. Let me just write it down.
Did you ensure you did get everything?
No. I skipped all the steps. We're still in the blend.
I'm supposed to do all this, but now it's consistent. Yeah. So the work here is it's part of the yeah, we're kind of weird.
I thought it was going to be
Yeah, that was the no, but I mean like they're on the spot about the price of solar. How do you compare it to the water? You know, involves
Okay, so I hope you filled in the steps in between. What we have is that the vector V is going to be the cross product between U and K because they want the line to be perpendicular to both of these. So do the cross product of them, we get this vector. And then once we have that vector, that's your ABC. A, B, and then C, 0. So, and then you have, like Joe said, R0. 0 to 1. Awesome. One more. Let's find something with line segments. So line segments will have those finite. There they are. 28 looks sufficiently disgusting. So what's the line segment between -1, -8, 4 and -9, 5, -3? Now, line segment, guys, is still a straight line, right? You still have to find the full problem, find the equation of the line, and then you have to find the two t's, right? Where it starts and where it ends. So you have to find t equals a number and then t equals another number to give that range. So the first part of the problem is exactly the same as the first problem we did. You just find the equation of the line. And then the new part is to find those two t's. So I hope you all have the line already. -1 minus 8t, -8 plus 13t, and 4 minus 7t. We all good there? All right. So now we have to figure out for which t we are going to get -1, -8, and 4. 0, right? So you can literally pick the first value and just match them. All others have to match. Otherwise, something is really wrong. Or we disproved mathematics, we pack and we go home. So -1 minus 8t equals -1 will yield t equals 0. So t is going to go 0 on the left. And then we're going to pick again this one and that one to check the end side. So that's going to be -9. So we have -1 minus 8t equals to -9. What's t? 1. So line segment, this is the answer. Not just the interval. You have to have a line and then that t part. Happy? All right, one more. Skew lines. A pair of lines in third-dimensional space, R3, are said to be skew if they are neither parallel nor intersecting. Determine whether the following pairs of lines are parallel, intersecting, or skew. So, if you observe this line here, right at the edge, it's a line, all right? Now, here's another line. These are parallel lines now, right? Spacing between them is always the same. This is where they intersect when they touch. But then also, this line will go forever that way, and this line can go like this, let's say. They miss each other. They're not parallel, they don't intersect, they just miss, right? We want every flight to be skew all the time, right? So, and then hopefully parallel for landing, because So how would you deal with that? You get set of two equations, and you are supposed to figure out. So here, problem 52. R of t is given as 4 plus 5t negative 2t 1 plus 3t, and then capital R of s, which is a different line, 10s 6 plus 4s and 4 plus 6s. So the easiest one to answer, obviously, is if they're parallel. What is the requirement for parallel lines in algebra?
Have to have the same slope.
Have to have the same slope. So what would be the requirement for parallel lines in 3D?
They have to have the same v vector.
They have to have the same v vector. Now we have to understand that v vector is just the direction, not a magnitude, right? That magnitude doesn't matter. So we have to make sure that they are, right, scalar multiples of each other. If they are scalar multiples of each other, then it's the same vector, same direction. That way, that means they're parallel. So first extract vector ABC from both and compare them. See if they are multiples of each other. If they are, lines are parallel and we're done. If they're not, well, then we're going to look for a possible intersection. So what is the vector lowercase v? Come on, don't be shy. Vector v. 5, -2, and 3. So those are the values in front of t. That's where the vector v, ABC is. How about capital V for the other one? 10, 4, 6. So now you see that one vector has one number to be negative, the other one has nothing. So they're definitely not multiples of each other. So I'll write that in blood. Since V and V are not scalar multiples of each other, lines R and R are not parallel. So we would have to have that situation. Now obviously something like this is, the only reason why I wrote it is because if you ever review your notes or the notes I upload, you know why we eliminated parallel. What are we going to do for intersection? Do they intersect? How would you compute something like that? What has to be common for both of them? How are we all here? Yeah, and they sign up for the class again. Yeah, I get it.
They intersect because they're not parallel and they're intersecting.
That's two-dimensional.
Yeah, but no, it would be fair if I choose boxer. So, oh yeah, flatland 2D. You're right.
Oh, I missed that part.
Going back to this, so what has to be the same for both lines in order for them to meet in space? And then my follow-up question is, how come we're here? To help you think about it. Come on, guys, Calc 3. Let's keep moving.
I guess it's that you can see the intersection of the various lines they have. Something like that.
Well, what about T? Yeah.
Oh, what's that? Can we somehow change S to T.
Why would you?
But then we can try to
How do you measure your time?
send it to
How do you measure your time?
J
Wrong person to ask. How do you know what time it is?
Look at a watch.
You look at your watch, yes, and that watch is the same as my watch, hopefully, right? So, time t for line R, right, and time s for line capital R need to be the same value. So, if the same value, which is 7:56 now, and so that's the same time for every single time and same position in space, which is this classroom. So there's the intersection, okay? So all of our paths intersected here. Remember, each one of us is a vector stretching from home to here, right? And we happen to be all here at the same time, right? In the same location. Just made this point to be kind of the whole room, right? So we don't actually have to pile up here. So the idea is that if you get these two to be the same and you get the same point, they intersect at that point. Good. So what do we do? How do we achieve that? No. Sim, right? So 4 plus 5t is equal to, say, 10t, right? You will get a value. And then just check if that value will make the other two happy. If not, it's not going to work. So what do I have? 4 is equal to 5t. T is equal to 5 quarters. So I change this t, right, s into t. What happened? That's what I said. Please pay attention. It's 0.8. So at 4/5 of a second, the first two coordinates are going to meet. But that doesn't mean in a 3D space that we're actually there, because we have to match these ones as well. So now, plug 4/5 everywhere and make sure that they all work out to be the same number. If they do, we got it. Do they? No? Keep moving. Done. So 4/5 didn't work. So you used one of these to calculate where is the coordinate where they would meet if the time is the same. And since that time didn't work in the other two coordinates, tough luck, right? So it's a miss. Awesome.
So you don't have to check for all three?
No, you just check for you calculate 4/5 on the first one, and then you check in the second one. Second one didn't work out, you just look at it. Well, I didn't write it, I should write it. So we calculate 4/5 from the first one, and then I plug 4/5 in the second one. What do I get? I get that -2 times 4/5. I'm asking myself if that's the same as 6 plus 4 times 4/5. On the left-hand side, you have a negative number. On the right-hand side, you have a positive number. So the y coordinate is not going to match. So we found the common time for x coordinate, and then the y coordinate was divergent already. So we don't even check for the z component because we found that y doesn't work. There's no reason to push forward.
So you don't have to check that, like, for the y, like, when they put the t to b, and when the y is equal to each other, and then try that on the other two, and then do it again.
Why would that work?
I don't know.
Something to do on Sunday. What else are we going to do? Well, that's it. Now let's take a look at some other cool shapes. So this is all straight lines. I am not going to cover limits in this section. We're going to go for a short break, and then when we come back, the second section is on calculus of these vector valued functions, and that's where we're going to do limits and derivatives and integrals in the same section. So I'm going to skip on limits in 11.5 and just add them to 11.6 instead. It's calculus, limits. The other example of this vector valued function would be helix. So helix looks like this. And if you draw the helix first, right, and then you put some coordinate system there, it's going to be much better than if you draw a coordinate system first and then try to draw the helix. Usually, if you put a line like this and then try to go rapid, it'll go like that. It's just bad. So what do we have in this case? The important thing is to kind of be able to mentally deconstruct these pictures when you look at them from different angles. I used to imagine a box around the object and then look at the side of the box to see only one perspective. So if I'm to put this in a box, this helix, and look from the top, the only thing I'm going to see is the circle. All right? So top view is only going to give me a circle. And the side view, if I'm going to look at this, it's going to give me it's difficult to draw, but side view is going to give you something like that. So you say, all right, can I simplify this? If I just ignore the back and I just look the front of it, it might look like this. Simpler version. So you go and you say, all right, how do I construct this three-dimensional vector valued function which describes this thing? So we see that from the top view, which is obviously projected onto xy, the xy plane, which is the floor, has a circle on it, and we know from chapter 10 parametric equations for the circle, which are what? Let's say that this stretches out to, I don't know, 3. What are the parametric equations, parametric set for circle? What are my chapter 10 experts? Yeah, chapter 10 experts. Let's go. Yes. No plus. 3 cosine t and then 3 sine t. So this is think of this as this is your x equation, this is your y equation. X equals and y equals. And all I need now is the third equation, z equation, which is the new feature This is what I said, that your Calc 2 chapter 10 gets upgraded into Calc 3. Whatever in Calc 3 has a circular shadow, when you shine the light from the top, put any kind of object, I don't care what it is, put that object on the ground, shine the light on top. If it gives you a circle on the bottom, your parametric equations start like this, right? Because that's the circle, x and y, parametric equations. And now we just need to figure out z. Now, that depends on how this rises. It can rise linearly, in which case you just put t and walk away. Or it could be t squared, could be e to the t, could be whatever other thing, right? So if it's nice and constant, right, the value rises. So as your value t is, let's say, going from 1 to 10, starts at 1, and it's rising up to 10, right, as the helix goes up. So in this case, we're going to put, say, t for the simplest one. If it's a constant, just number 3, well, that was just going to be a circle. There's not going to be helix, right? Because your z is flat. It's 3 or 5 or whatever it is. And there will be no room for helix to grow up, to grow, right? To go up. So we have, and then it can go faster. It can go slower. So you can have, if z component is e to the t, you know, a helix might start busy and then just, whee, right, grow really quickly. It's still going to spin, but it's going to spin very slowly. It starts spinning fast and then, right, does that. Obviously, what you guys did is you installed Mathematica on your computers. Obviously, when you go home tonight, the first thing you do is going to graph all of these in Mathematica to figure out how it's done. Now, obviously, you will find on YouTube or you will find on a website somewhere how to graph parametric equations in Mathematica. And then you're going to keep changing this t to t squared to e to the t to see the differences between those graphs. Because your jobs in engineering down the line is producing that. You look at the object and you say you're designing something, and then you need to figure out what the function is. That's your job. It's not going to be to integrate. Never going to be integrate. Is anyone a math major? So your job is to integrate, right? So they can teach others to integrate. What I do, right? But as engineer, software that costs $2,000, you plug that in, integrate for you, done, right? You know what you need to know what the integral gives you, right? The energy, right? Area under the curve and stuff, and what are the applications of that? But no one cares if you can do integration by parts, because that's not going to be your job. But what your job is as the engineer is to see this thing and say, oh, but that's the equation for it because I engineered that equation. I see the circle when I look from the top, x and y, and then it rises linearly steady, so that's t. Maybe it's rising faster as 2t, maybe it's t squared, maybe it's e to the t. And you really can't get any of these things until you actually sit down and spend time. And you all have on that syllabus, right, $1,000 gift, which is Mathematica. So you should install that and spend some quality time. Okay? Tonight, what else are you going to do? Well, it's going to work. It's going to be 9 o'clock. Right? Right. Yep, that's it. There are many other things you'll try, and then we'll talk more. So we'll restart the stream for the next section. Bye.